Hi, I'm Garvin Heath. I'm from the National Renewable Energy Lab. Thank you to Karsten for inviting me here. It's my first time at AGU, and these sessions are really exciting for this area of work. And I'm someone who uses a lot of the outputs of the measurement folks who are mostly represented here. And so maybe that was an interest of Karsten to have this work presented. It's about life cycle assessments and our use of information about methane emissions in particular to examine the contribution of greenhouse gas emissions from different power generation sources, including natural gas. So of course we're interested in this because the methane leakage as the, let's see if I can get the methane leakage on the x-axis here has a large driver of trying to understand the climate or the greenhouse gas emission consequences of a choice between coal or gas. Coal being this sort of gray band here with two different efficiencies and a 20-year or a 100-year global warming potential for methane, but regardless of that choice, you can see that it's important, this methane leakage characteristic. And of course, we have an inventory showing us about down here, so pretty clear benefit from gas, but then we have measurements taken at certain times and at certain places that would indicate that at least in those times and places we have methane emissions rates higher. So we're in this circumstance, which of course is driving a lot of your work, trying to understand the situation better, and life cycle assessment is one way to put that in context. You all are probably much more familiar with inventories. Inventories, to contrast with life cycle assessments, are cross-sectional in nature. They take over a certain period of time and a spatial boundary, sometimes an industrial sector boundary, and look at emissions of a particular pollutant or set of pollutants over that time. Life cycle assessments, to contrast, are looking at more of a longitudinal framework. That is, we're starting with a certain amount of, let's say, gas that's produced coming out of the ground, and then we're tracking, in this case, greenhouse gas emissions as that gas moves through the system all the way through to its end use, and then we're normalizing by this unit of end product, here a kilowatt hour of electricity generated. Life cycle assessments have been around for many decades now. There are some codified standards for these, International Standards Organization, ISO standards, but there's still some methodological issues that persist. Nevertheless, it's been selected by the IPCC, at least in this special report on renewables, and it also was featured in the AR5 as an appropriate basis for consistent comparison, especially amongst different energy choice options. So for instance, renewable sources versus conventional energy technologies. And this is just a sort of a diagram of, we're counting for a power sector technology, for instance, how to build a power plant, operate it, and decommission it through its full life cycle, but then importantly track the fuel that's being used to operate it. But despite having codified standards, there's a lot of variability in the results of individual life cycle assessments. This was a systematic review that we provided to this IPCC special report on renewables, looking across all the different electricity generation technologies. You can see here the counts of references and individual estimates that came from those references. And you can see that for certain technologies, some highlighted like biopower, but also these fossil ones had a pretty wide range of variability due to many different conditions. I want to highlight here also that for natural gas, at the time that we conducted this systematic review, there were no life cycle assessments for unconventional gas. And of course, a question that's emerged is whether unconventional gas, for instance shale gas, had a different characteristic of life cycle greenhouse gas emissions compared to conventional. So since that time, there's been an emerging literature on unconventional gas life cycle assessments. And so started with Bob Howarth at Cornell, and then went through to across many different studies and techniques and focus areas, et cetera, through to a study that came out of ExxonMobil. And their conclusions were really quite contrasting. Of course, if some of you are familiar with this literature, starting with Howarth saying that gas was worse than coal, and then sort of bouncing around pretty consistently as gas less than coal, but bouncing around between whether unconventional or conventional gas had higher life cycle greenhouse gas emissions. And it's important to say that at least part of this inconsistency is driven by differing methodological choices. And these studies themselves were not the motivation for this project, but understanding that just in general about life cycle assessments motivated this work sponsored by the Department of Energy, which we've been working on for the past 4 or 5 years now, which is a meta-analysis, what we call harmonization, or a meta-analysis to try to adjust the results of prior life cycle assessments on a given technology to try to ensure some greater consistency so that then we can make more consistent comparisons between the results of one study or another, and also to try to support some more robust decision-making around those technology categories, to try to give us insight also into the drivers and influencers on the results. So for natural gas, then the harmonization steps, not fully listed, but the most important ones were to adjust those results to use a consistent global warming potential. We did that on a 100-year basis, and then updated to the AR5 value. It's important to make sure you're including the same set of processes and the same boundaries on your system. So those different life cycle phases that I showed before, as well as some important activities such as liquids unloading and recompletions were things that we adjusted. And then finally, because we're talking about the application of gas to generating power, the power plant thermal efficiency was an important characteristic to try to make consistent. And so we had 2 recent articles, one focusing on the literature, the much broader literature on conventional natural gas, and then one that focused on this more recent literature for unconventional natural gas. And then we had many, many others that are looking at the other power generation systems that all appeared in a special issue of the Journal of Industrial Ecology. These are the results of the harmonization of these shale gas life cycle assessments. The details aren't really important here, but you can see that we start with a published value, and then there was an adjustment through this harmonization process. So sometimes there was a relatively small adjustment due to the steps that we took. And sometimes there was a relatively large adjustment, but in general, this shifted more towards that one-to-one line. And the y-axis, we have the conventional, or sometimes actually included unconventional, because it was a full domestic gas sources, and then shale or unconventional sources on the x-axis. So that one-to-one line means that you're getting closer to an equivalent estimate from each. And then this is sort of the summary of those same results, now not looked at individually by the paper or estimate. So that after methodological harmonization, these unconventional gas, the estimates of life cycle greenhouse gas emissions used to generate electricity from the unconventional gas sources here, much smaller data pool, looked very similar to conventional. And both of them, when comparing, at least in the median estimates, looks what people have found well before, and so we're finding it in the recent literature as well, to be about half that of coal, characteristic estimate of coal, with a very high number of papers that looked at coal before. But one thing that we did in this paper was to try to examine some of the sources of at least sensitivity to these results. And so we broke that down by 3 different important activities found through uncertainty contribution analysis and other papers, to be the well completion activity, recompletion if that occurred for a particular well, and then a liquids unloading activity. And I don't have time to explain those as industry terms, but you can ask me a question later if you want to. And then one important parameter, so then we divided these up into different contributors to those, such as the estimated ultimate recovery of a well. That's the lifetime production of a well, which is an important normalizing factor in life cycle assessment, emissions reduction technologies and assumptions around those, the well lifetime itself, and then the emissions factor from that activity. And we developed a probability distribution function for EUR based on the active plays, shale plays in the US. So that's why you can see that sort of squiggly line across here. And what we found was that this liquids unloading activity had the greatest sensitivity, or the life cycle greenhouse gas emissions had the greatest sensitivity to assumptions about liquids unloading and the emissions factor in particular. And this emissions factor was also a probability distribution function that we had developed from some granular operator-reported data from a large sample. And so at least in certain conditions, we found that the sort of worst case, or towards the worst end of the cases for unconventional gas, for shale gas, got into the range of the best performing cases for coal. And so one of the take-home messages from this was that we need some more empirical research, which of course is with your community, to try to verify and clarify the emission sources, their prevalence, and also their variability, so then we can, in these contexts, try to synthesize that to help inform some of these energy choice decisions. Acknowledging my co-authors from this work and funding, and open for questions. Thank you. Well, it would differ, and it would differ primarily along the lines that you saw from the first slide there. So that shifts your balance, so your sensitivity to this leakage rate becomes a lot less when you start talking about the 20-year goal warming potential. And Alvarez, in a PNAS paper in 2012, proposed a TWP, technology warming potential. There are many different metrics that are out there that you could examine and choose. 100-year has been chosen by both the IPCC and many others as the sort of consensus basis that balances both short and long-term impacts, but there's a clear argument for why one would be concerned about shorter-term impacts, and therefore you might choose to use the 20-year.
Are there any more questions?
I thought there was one other hand, but maybe that.
If there's not,
Okay.
Can I ask a question? I noticed
sure.
on slide 8, where you showed the results of your harmonization, was there a trend of, who was doing the research, whether they went up or down?
Who was doing the research? No, I wouldn't say there was. There was not a discernible trend. I don't think I really examined that in particular. Some of it depended on the year they did the study, because there were certain things that were known at certain times, and so there were certain adjustments that had to be made for older studies, different from newer ones in a couple cases. They're largely drawing from the same data sets. They're almost always getting a lot of their information anyway from the US EPA's greenhouse gas emissions inventory. And they just put it together in some different ways, and making certain other assumptions can yield these quite variable results, especially the comparisons. So I'm not going to say that there's like something different about who was doing the research.
No, I don't want to put you on the spot. I was just curious.
Okay.
So we're going to stay on time? Thank you.
Yep, great. Thanks.